Okay, in our final chapter of this year, we are going to look at global change. This particular chapter is going to look at climate change, the greenhouse effect, and then we're also going to review the ozone just a little bit with this. Okay, so this slide does a really good job of talking about three different layers of change. And whenever you are answering, especially a free response question, please be sure that you pay attention to the words that are used in the question. For example, in the top box, you can see where it talks about global change. These all are things that happen as a result of sea level rises. You increase extraction of fossil fuels. The biogeochemical cycles are disrupted. Biodiversity decreases. So those are things that affect large-scale change. Okay, and then if you look, it is also connected to global climate change. Okay, global climate change has a specific listing of things that happen as a result, or that kind of drive it. Increased storm intensity is something that we expect to see as a result of global climate change, for the simple fact that oceans will be warmer. If the oceans are warmer, they can fuel bigger storms. Definitely altered patterns of precipitation and temperature. And this doesn't necessarily mean that every place that's cold is going to get warmer. That's a false statement that a lot of people think of. Everybody thinks, oh, climate change is great. Every place will be warm. And that's not necessarily true. What's going to happen is you'll start to see bigger extremes. Some places will actually get colder and some places will actually get warmer. Places that typically get a lot of rainfall may get less rainfall. So just kind of keep in mind that the altered patterns of precipitation and temperature don't necessarily sway one way or another. Altered patterns in ocean circulation. With that one, that is tied to increased storm intensity, and it is also caused as a result of glacier meltwater, and also iceberg melts. As both of those types of frozen water are freshwater. So as they melt and run into the ocean, they affect the salinity of the ocean water. And as a result of that, it will also impact the circulation of the oceans. Not to mention, it will also, if the oceans are warmer all the way around and you don't have as much cold water, that turnover from north to south is not going to happen as intensely as it does today. And then so, again, going back, a change, and then global warming is simply nothing more than warming of the planet's land, air, and water. Reduced cold spells, increased heat waves, and vice versa. You may see intensified cold spells as a result of this as well. So that's just kind of a brief overview of global change and how it's tied into climate change and global warming. This is a slide that you probably should be pretty familiar with in the big scheme of things. Climate change, the greenhouse, or I should say climate change and the greenhouse effect are tied together. The greenhouse effect is extremely important to Earth. It's what makes Earth different from all other planets in the solar system, because we have the right amount of greenhouse gases that exist in our atmosphere. We can absorb some of the solar radiation that reflects off the Earth, and that solar radiation warms the Earth's surface. Some of it is reflected back out into outer space, but the majority of it is held within those greenhouse gases and keeps the Earth warm. The concept of the greenhouse effect is not a new idea. It was introduced in 1896, and it was basically looked at as a very positive thing that the Earth needed to help life exist as it does. When looking at climate change and the greenhouse effect, basically what we're looking at is how humans are enhancing the amount of greenhouse gases that exist in the atmosphere. There is no if and buts about the fact that our presence on Earth has enhanced the amount of greenhouse gases, which again holds more heat in. Again, climate change naysayers will argue that, well, the Earth has been ice-free before, and the sea levels have been higher before, and all of that is true. We've been way warmer, and the oceans have been way higher than they are right now. Sea levels have been way higher. The only concern that needs to come into play is the rate at which this change is happening. Those past climate changes were attributed to several things. We'll talk about those here in a minute. So climate change is nothing new due to regular patterns that the Earth goes through. However, how fast it's changing right now is a definite concern. Okay, so looking again, 100% solar radiation comes in. You don't have to know any of these numbers, but it is kind of nice to just realize that a big chunk of this gets absorbed by the surface. And again, this helps warm the Earth's surface and, the upper part of the atmosphere that is close to the Earth. You can see that a small percentage of it gets reflected. Some of it also gets reflected by clouds. Some of it ends up back into the atmosphere. But the atmosphere does also absorb some of this incoming solar radiation, about 19%. So if you look between the 51% and the 19%, you're roughly looking at about 70% of the incoming solar radiation spends most of its time in the lower atmosphere and being re-radiated from Earth's surface or absorbed at Earth's surface. As I mentioned before, previously we have been way warmer and we have been way colder than we are presently. And this diagram just kind of different way of looking at it. Incoming solar radiation, it kind of shows you in a different way what gets reflected, what gets absorbed by clouds, and then, talks about the role of the sun and the greenhouse gases in terms of keeping the Earth's surface warm. The thing as you look at this, is to realize the little box that they kind of have drawn in here, right, especially right in through here. This is where the greenhouse gases are in the atmosphere. But as I mentioned before, climate change and the greenhouse effect are not new. Past climate changes have been attributed to things such as changes in the length of the Earth's elliptical orbit. And again, the Earth orbits in kind of like a football-shaped pattern, and that pattern changes about every 100,000 years. The Earth also tilts on its axis as it rotates, and that tilt does not stay consistent. It kind of moves a little bit, and that happens about every 40,000 years. And in addition to that, as the Earth tilts, the axis also wobbles. So that wobbling can also affect the amount of solar radiation that the Earth receives. Solar output doesn't stay consistent. Now, you've probably heard of solar flares. So the amount of energy that the sun gives off fluctuates, and as a result, the amount of incoming solar radiation that we receive also fluctuates. Other natural events such as volcanic eruptions can influence climate as well. For instance, large volcanic eruptions such as Mount St. Helens in the 80s put ash into the atmosphere that, thanks to the westerlies, ended up in Ohio. The weather in and around that area was impacted for several years as a result of all the dust and the ash that was in the atmosphere. So when all of these things kind of, align, they can significantly affect the weather for long periods of time. 40 million years ago, Antarctica had no ice on it. It was actually forested, and global sea level was 70 feet higher than it was today. 40 million years ago, the Earth was ice-free completely. So the concept of being ice-free is not new. The difference is that humans weren't there. So as a result, there were no inconveniences to us as a result of these changes. But with us being entered into the equation, we've definitely impacted the rate at which climate is changing. All right, so none of this should be a real big surprise to you. Most of this is a pretty big review. Shortwave radiation passes through the Earth's atmosphere. Some of it is absorbed by the ozone layer, which we talked about in the last chapter. And it plays a role, especially if CFCs are in the ozone, in destroying our ozone layer. So as that radiation passes through, the Earth's absorbed, the actual Earth's surface absorbs some of it. Some of it is reflected back out into the atmosphere. Where it bounces around, some of it, again with clouds, some of it then exits back out into outer space. So the 80% that's reflected is absorbed by greenhouse gases. And those greenhouse gases are responsible for keeping the Earth's surface warm. So the whole idea behind that reflected radiation and the radiation that's given off that's been absorbed from the Earth and then gradually gets released is held at the Earth's surface instead of just all being let loose back out into the atmosphere. And that is the greenhouse effect. Again, I said this in the last chapter, but please, please, please do not confuse the greenhouse effect with ozone. And we're going to do a quick little review of ozone. You saw this picture in the last chapter. This is the hole over Antarctica as of September 10th, 2000. The good news is that, as I mentioned before, this hole has shrunk significantly with the banning of CFCs through the Montreal Protocol. But when we talk about the ozone layer, we talk about the ozone hole, okay, this is a depletion of the amount of ozone in the stratosphere. So we're not talking about bad ozone that forms in the troposphere. Most of this typically also collects at the poles. So we see these holes developing at both poles. The one over Antarctica is quite a bit more intense than the other one. And these are caused by CFCs, chlorofluorocarbons. And you may want to go back and revisit the chemistry behind how the chlorofluorocarbon bonds with the oxygen and then kind of stays stuck there. The key thing and the connection between ozone and talking a little bit about greenhouse gases. The ozone is a greenhouse gas. All right. Ozone does not cause greenhouse, and greenhouse does not cause ozone. Ozone is just a greenhouse gas because it does absorb the UV light as it then gets broken apart. Unfortunately, the hole in the ozone has a slight cooling effect on the Earth because the ozone absorbs UV light, and then that means that there's less ozone, less UV absorbed, and as a result, if there's less ozone, then there's less heat that's held closer to the Earth's surface in the ozone layer in the stratosphere. Ozone and greenhouse, once again, have a lot of commonalities, but one does not cause the other. All right, so if you talk about greenhouse gases causing a hole in the ozone, I said this in the last chapter, you're making a huge error in terms of speaking about the two of those. So please make sure you keep these separate in your mind. And again, I mentioned this already. Ozone is a greenhouse gas, and it's in the good ozone is in the stratosphere. The bad ozone is in the troposphere. So that's what this is referring to. The ozone that's formed in the troposphere is a greenhouse gas. It does absorb and contribute to climate change. The good ozone that's in the stratosphere has nothing to do with climate change. And that's kind of what this next slide highlights a little bit for you. The stratospheric ozone is good stuff because it keeps out harmful radiation. The tropospheric ozone is an air pollutant and it acts as a greenhouse gas, so that's problematic. Okay, so again, just kind of to recap, you should be able to explain what the greenhouse effect is. The Earth would be cold, barren, lifeless rock without it. And then you should be able to talk a little bit about the difference between ozone in the troposphere versus ozone in the stratosphere. Which one's good, which one's bad. How does the good ozone get broken down through CFCs? So it's kind of something that you might want to go back and revisit just a little bit. So major greenhouse gases. We're going to have to pay attention to water vapor. This is one you're familiar with. This is one you're familiar with. Nitrous oxides are probably one you may want to put a star by because you're not super familiar with that one. And then we just talked about ozone. So ozone in the troposphere is a greenhouse gas, but ozone that exists in the stratosphere is not an ozone gas. So all of these have fluctuated. We're going to look at a couple of graphs in a few minutes. You'll see spikes around 11,000 years ago when agriculture really, got a base, about 8,000 years ago when we started clearing forests for more agriculture and domestication of animals. You'll see another spike of some of these. And then about 5,000 years ago, there's also another spike when rice started being a major agricultural product because lowlands were flooded and the decaying material in lowlands released some of these greenhouse gases. So again, we've seen fluctuations in greenhouse gases, but since man has been around on Earth, some of those fluctuations, and especially with burning fossil fuels, are happening much more intensely now. The key thing in this graph that you need to see, well, first of all, to point out, we have surpassed 400 parts per million. I believe we're up close to 420 at this point. You can see methane, nitrous oxide, chlorofluorocarbons. But the thing to point out down towards the bottom, and with methane too, is that the global warming potential for these at very low concentrations is really high. So carbon dioxide sits at a 1. So if I kind of make an analogy here, carbon dioxide is like putting on one blanket in a chilly room. But methane is like putting on 3 blankets in a chilly room. It's going to keep you much more insulated. Nitrous oxide is like putting 20 blankets on, and then chlorofluorocarbons are like putting 1,000 blankets on. And if you notice, these all have double whammies because some of these that have higher warming potentials also stick around in the atmosphere longer, which is not good because they can have longer warming periods then. So when we talk about methane release, especially from things like landfills and rice production, that methane that is released through those decaying materials, definitely has potential to throw a bigger blanket on than carbon dioxide. Methane, nitrous oxide, and chlorofluorocarbons don't get enough press, in my opinion, because they're much more dangerous when we start looking at their warming potentials. Water vapor, most is pretty self-explanatory, most abundant greenhouse gas in the atmosphere. It's the greatest natural contributor to global warming, but again, that makes sense simply because it's the most abundant. It also exists or is released into the atmosphere through evaporation and evapotranspiration. Remember, evapotranspiration is the release of water from plants. Methane. This is a nice little picture. The picture that you see down here, the gentleman is golfing actually on a landfill. Methane is produced when there's not enough oxygen present to help break down the material that's there, and then they would produce CO2 naturally. So as a result, the organisms that are in things like landfills break this down anaerobically, and methane is released. However, methane has some really stringent air quality standards in terms of being released in the atmosphere because of its potential. So its warming potential, I should say. So as a result, many times you see this in the trip to the landfill, the carbon dioxide or the methane will be burnt. And the process of burning methane actually breaks it down into carbon dioxide. So it's kind of not necessarily the best scenario in terms of what to do with methane. Methane can actually be burned as a fuel if the facility, for instance, if the landfill would have cars that could run on methane, it could actually be used as an alternative fuel. Wetlands, again, are the biggest natural source of methane. And the reason why, if you think about it a little bit, all of the decaying material, there's not a lot of oxygen in the water. Most of the oxygen's been used by the decomposition process. So again, as bacteria and other organisms that are anaerobic break down that PD material, you end up with methane being released. Agriculture also plays a role in methane. In the guts of things like cows, their stomach is called a rumen, and they work in really low oxygen environments to break down feed and to break down other things that cows and other rumens eat. These are basically things that have 4 stomachs, and as a result, when they pass gas, a lot of times the gas they pass is methane, simply because that's the way their internal digestive system is set up to work. Nitrous oxide, go back to the nitrogen cycle. So denitrification is the breakdown of nitrate into nitrous oxide gas. And you can see that in the nitrogen cycle, this is a typical part of the cycle. However, humans have intensified this because synthetic fertilizers create an excess of nitrate, as does animal manure. And as a result, there ends up being more denitrification than there would be typically. So unfortunately, humans have provided some of the input materials to kind of enhance the production of nitrous oxide, which again is something we don't necessarily want more of. We talked about this slide already. And we did that in relationship to the global warming potential. But again, coming back to chlorofluorocarbons, they have some wicked consequences, not only in in the case of greenhouse gases, but also the breakdown of ozone. These materials, these chemicals are not used in the refrigeration or air conditioning or aerosol cans anymore. Most of them have been replaced by something else. In most developed countries, they've phased out the use of CFCs altogether. All right, so talking a little bit about carbon dioxide, lots of sources of carbon dioxide. Volcanic eruptions, burning fossil fuels. So this one and this one are probably man's biggest influence in terms of releasing carbon dioxide. When we talk about burning fossil fuels, you'll often hear this referred to as old carbon. Oil, natural gas, coal were all things that a long time ago, when they decomposed and were compressed, took carbon out of the atmosphere. So by burning them today, we're actually introducing old carbon that was stored a long time ago into the atmosphere. Deforestation also releases carbon into the atmosphere, especially when those trees are burned. However, if they're not replanted, then unfortunately the carbon dioxide that trees would take out of the atmosphere to do photosynthesis also contributes to that. So when we cut down trees, depending on whether we cut them down and use them for a product or just cut them down and burn them, if we're cutting down and burning them, that's kind of a double whammy in that particular scenario that doesn't end up being, obviously very positive. Decomposition of manure in the presence of oxygen a lot of times will also contribute carbon dioxide. And so that would be something that, again, humans enhance through agriculture. So if we have a significant amount of animals in an area and that manure is decomposing, it will release carbon dioxide in that process. Two things that to kind of maybe add to this slide, oceans and forests act as huge carbon sinks. And we've talked about carbon sinks before. So carbon sinks are our oceans and our forests. So obviously we already talked about forests and the role they play with photosynthesis and absorbing carbon dioxide. But oceans also absorb carbon dioxide. And unfortunately, the solubility of a gas decreases as temperature increases. So as the oceans get warmer, they're not going to be able to absorb as much carbon dioxide in the long run to kind of help us out. Another term that you should definitely probably jot down here is what's called a tipping point. Tipping point is the point of no return. So you'll, especially with carbon dioxide, hear scientists talk about 400 parts per million or 450 parts per million is kind of the tipping point, the point of no return. And what they mean by that is, at that point, the damage that will be done by the carbon dioxide in the atmosphere is not something that scientists think we'll be able to recover from. On a positive note to that, at least I think it's positive. That tipping point number always continues to creep up. Several years ago, the tipping point was considered to be 400 parts per million. Now I know that it's crept up a little more towards 450. So hopefully that means that humans are finding ways to deal with the carbon dioxide that we're putting in the atmosphere. However, we also have to consider if the environment that we live in can deal with that amount of carbon dioxide. All right, so just to talk a little bit about the gentleman who is kind of given credit for first measuring carbon dioxide levels and saying, hey, look at this trend that's going on here. And he did this in an observatory in Hawaii, and he picked that area simply because it was very remote, and there were no fossil fuel power plants or anything like that. So he felt that the readings he would get would be fairly accurate. He's the first person to say, hey, you know what? Look at what's happening to carbon dioxide and look at what's happening to temperature. So he's the first person, again, in 1958 to maybe throw up a red flag and say, hey, I think maybe man's playing a role in terms of warming the earth. And then again, once he kind of threw up the red flag, more work was done and starting to look at, temperatures alongside of carbon dioxide. And you can kind of see the more purplish is annual averages, and you're comparing that against a 5-year average. You can see that they mirror themselves, pretty much side by side. And it makes you wonder when you look at these, the connections between. So since 1880, global temperatures have increased about 0.8 degrees Celsius. I also know that recently that number was bumped up to 0.9. So we've seen a little bit more of an increase, and that number has been updated. So again, when we think about climate change, good things, bad things. Shipping lanes open up in Russia, Canada, Alaska, so we end up with more commercial fishing for the simple fact that, there's no ice there, so we can get more ships in. Unfortunately, though, if you're an aquatic organism that lives in an area that is temperature specific, water warms up, and we're probably going to lose those species. Tourism is kind of a good and a bad. I mean, if you go to Glacier National Park to see the glaciers and the glaciers are gone, how does that impact tourism? On the flip side of that, if places that are no longer glaciated, people can now get to, tourism may increase. If there's no glaciers that exist because they've all melted, there'll be no meltwater, there'll be no runoff recharge. How does that impact agriculture? Increase in sea level means that we lose our barrier reefs, we lose, low-lying islands. Areas that we grow rice are typically along the coastline. So those are all things that go away. But on the flip side, in terms of economic downfalls, you also have to consider coastal tourism and the damage to all the vacation homes that are that close. Saltwater intrusion we talked about earlier in the year. Warmer temperatures mean you get more pests. The range of things like mosquitoes increases. So when you talk about climate change, you should be able to create a nice list of both positive and negative environmental, social, and economic factors that could result. So if temperature goes up, here's a positive environmental scenario, here's a negative environmental scenario. Make sure with the environmental scenarios, you don't talk about humans, okay? So once again, if you might want to go back, do a little thinking, dig through the book, but you should, definitely be sure that you create a list so you can talk about the environmental, social, and economic factors for that. Again, just another graph which kind of shows time and CO2. I think that it is really, really hard to ignore the end of this graph where CO2 just blows up. And this is all tied to the Industrial Revolution and burning of fossil fuels as a major source of carbon dioxide, old carbon being burned and releasing that carbon dioxide. How do we know what greenhouse gas concentrations were in the past 400,000 years? Because no one was around with a little thermometer. So looking at fossils and changes in species compositions, knowing that certain organisms live, say, in a shallow marine environment, for instance, trilobites, and we don't see trilobites anymore. So it tells us that their environment dried up or it's too cold for them. Probably one of the biggest ways that we know these greenhouse gas compositions is to look at ice cores. Ice cores, as snow compresses, the ice captures bubbles of gas in it, and then scientists today can melt those cores and then measure greenhouse gas via those bubbles. So that's one of the major ways that we know past greenhouse gases. Another way are little organisms. Let me write this one out for you. Called Formaneras. Hopefully you can see that. And basically different species of these guys just like different water temperatures. So again, it's kind of going back to changes in species composition. So when temperature changes, they die off. And at that point, scientists can give a rough estimate as to what the temperature was of the oceans when those die-offs occur. So they're very useful in that regards. Again, just this graph mirrors temperature change in CO2. You can kind of see that the purple and the blue match up really well. So again, not necessarily saying causation, but you can definitely see there are some connections between the two. The next diagram that you see kind of shows roughly surface temperature changes based on predictions in CO2. So the top one looks at low increases in CO2 and then moderate ones and then high increase in CO2. And you can see that surface temperature changes significantly, the more CO2 that there is in the atmosphere. So that graph, again, that little picture is pretty easy to interpret. As you know, you kind of have to be living under a rock. Climate change comes with controversy. Basically, the question is, how much our temperature is going to increase for a given greenhouse gas, because it really depends on feedback loops. Scientists don't dispute that there's a connection between some of the fluctuations in climate that we're seeing and greenhouse gases. Scientists will not dispute that. Scientists will not dispute that the bulk of those greenhouse gases are coming from humans. Again, especially coming back to fossil fuel combustion being one of those major sources. Again, taking that data and extending it out to kind of figure out how much of a change is going to happen is what's in dispute. At the beginning of the year, we talked about feedback loops, and with positive feedback loops, you can kind of see that what you end up with are higher temperatures, and one of the things that can happen is you end up with more decomposition, and more decomposition gives you more carbon dioxide. So positive feedback loops, if you're not going to remember this, positive feedback loops are actually extremely negative. They push you further and further away from equilibrium. Another thing too, with higher levels of carbon dioxide in the atmosphere, you end up with more glaciers melting, so you have more land exposed. Land is a dark color. Dark colors absorb solar radiation. That warms the surface underneath glaciers also then warm up and melt more ice. So that's another example of a positive feedback loop. And again, it's really important to remember positive feedback loops are very negative because they continue to push you away from equilibrium. Negative feedback loops, on the other hand, pull you back into equilibrium. So if you notice, you have more plant growth, more plants, they remove more carbon dioxide. So you end up, again, with more plant growth, and you can see that cycle brings us closer to equilibrium by removing carbon dioxide from the atmosphere. When we spend a little time, kind of looking at the system as a whole. Carbon dioxide causes greater capacity for warming. When the Earth has higher temperatures, again, I already talked about this, solubility of CO2, that sink kind of gets broken. So they'll end up releasing more carbon dioxide into the atmosphere. So this is another example of a negative feedback in that particular scenario. All of these things, are pretty self-explanatory. You've probably heard of them somewhere. You should be able, again, to kind of think a little bit about and explain both the positives and the negatives in terms of environmental impacts, social impacts, and economic impacts of any of these things happening on the list. You are familiar with the Kyoto Protocol. And basically what happened is representatives from around the world decided that they needed to look at ways that they could control emissions that were contributing to climate change, to global warming. So at the summit, what they agreed to do is that all industrialized countries would agree to try to reduce their CO2 emissions, their greenhouse emissions, below what they had in 1990 by about 5%. And the year goal was 2012 for that. A lot of countries met that goal. Developing countries, they set a little bit different limits. Their amounts needed to be less than 1%. And if you think about why that's the case, are developing countries, burning a lot of coal? So you have to think about, this is a lifestyle difference. So developing nations contributed by agreeing to, limit their CO2 and greenhouse gas emissions, but it was significantly less that they agreed to reduce by. Unfortunately, and most of you know this, the U.S. was the only nation to not sign the Kyoto Protocol. Basically, President Bush was a little upset that the United States wasn't going to get credit for the amount of preserved areas they already had. The Kyoto Protocol wanted you to plant a few more trees, be a little more environmentally friendly. And when basically, the other countries who were at the table said, no, we expect you to come up with something a little bit better than that, President Bush said, yeah, thanks, but no thanks, I'm not signing this. So as this is an important part of history, so you definitely want to make sure that you're familiar with the Kyoto Protocol. One exciting area that definitely in terms of removing carbon dioxide from the atmosphere is carbon sequestration. Basically, this is an idea of how to take carbon dioxide out of the atmosphere and storing it in other places. You can store it in soil. You could store it in agricultural lands that aren't being used. Scientists are also looking at ways to capture CO2 from the air, and then they'll basically take that CO2 and compress it and pump it through abandoned oil wells or down into the ocean. And this is kind of what it looks like. It's a little bit easier to see. So you have a coal-burning power plant over here. It will still have its scrubbers, so it will definitely be sure that it's removing those NOx and SOx, so we don't have to worry about acid rain. But it also then will scrub for CO2. So over here you can see there's an abandoned oil field, and that carbon dioxide would be pumped down into coal mines or old places where oil has been removed or natural gas has been removed. It can even be pumped down into or below old saltwater aquifers that cannot be used anymore. They're even looking at ways to transport it out to sea and pump it into ocean bottoms or bottom rock layers underneath the seafloor. This is probably going to be fairly cost prohibitive, but the ones on land, we've actually spent some time doing. Countries overseas actually have spent a lot of money and are doing quite a bit of carbon sequestering through power plants. The United States had a plant that was sequestering carbon. It was an AEP plant in West Virginia. They had received a grant from the Department of Energy to actually put in the CO2 scrubbers, and they were pumping the CO2 down into abandoned or old rock layers through oil wells that were present in the area. So, this is definitely a promising way to remove carbon dioxide if we can't figure out ways to kind of lower the amount of carbon dioxide that we are putting into the atmosphere. So last but not least, as we wrap up talking about carbon dioxide, kind of circling back around with ways that countries are dealing with this, don't forget the follow-up to the Kyoto Protocol was the Paris Accords. And we all know that those did not end well, for the United States. The United States opted to pull out of the Paris Accord discussions and not participate in trying to figure out ways to reduce our carbon dioxide emissions. However, on a positive note, several states have taken up the guidelines and the kind of the standards that were set by the Paris Accords, and individual states are trying to follow through and reduce their greenhouse gas emissions in accordance with the Paris Accords.